say benzoic acid?
Benzoic acid is not so much a second substituent as it is a common name for a carboxybenzene. Do you remember on the first day when we did nomenclature and you called benzoic acid carboxybenzene? And then I said, no, that wouldn't be correct. I was wrong. Carboxy is a prefix term for the carboxylic acid.
What would you call it if there's another carbon in between the ring and the benzoic acid?
That becomes the longest carbon chain is 2 carbons. So that'd be 2-phenyl ethanoic acid or 2-phenyl acetic acid. Based on the name, what do you know? Benzene ring. Carboxylic acid. Does it matter where I draw my carboxylic acid? No. Yes. Yes, it matters that the product is 1,4 because of para. But when I'm starting, can draw it anywhere. I like that top right spot because it's actually really easy to draw the carboxylic acid from it. Most of the other spots, it gets really cumbersome. Para is that 1,4 relationship. So what is placed para? Methyl. Now, that should look apparent because you've got a para aldehyde carboxylic acid disubstituted benzene. By the way, this is not a compound I would ask you to name because one of those 2 groups would have to become a prefix. And I'm not so interested in you grappling how to make them prefixes because they feel really awkward and cumbersome. Both of these are ones that I encourage you to use their common name, benzaldehyde benzoic acid. So we could probably call it para-carboxybenzaldehyde or para-carbaldehyde benzoic acid. But either way, it keeps that 1,4 positioning. Naira, you classified this. What is happening in this reaction?
The aldehyde is being reduced.
Good. This is reduction. And the only reaction that we've seen for reduction so far, reduction of the carbonyl to an alkane, is the Wolff-Kishner reduction, otherwise called the hydrazine reduction.
Hydrazine is the N?
Yep, hydrazine is H2NNH2.
It's like an M peroxide.
Yeah, it's actually called a hydrazine because then you can substitute it.
Is that what a diazo is?
No, not necessarily. All right, that was reaction number 3, correct? Hydrazine reduction.
Mm-hmm.
Then an offshoot of this is the Clemenson reduction. Or, if you'd like to recognize it by its reagents, we're going to use metal and acids for this reduction. Once again, only reduces aldehydes and ketones. Why did we end up with a carboxylic acid in our first product? Because carboxylic acids cannot be reduced by Wolff-Kishner reduction. Same thing goes here. And to clarify that confusion, I forget, I think it was Cameron's question last class. Just because this is being classified in benzylic reactions, it's just being introduced there by your textbook. All aldehydes, all ketones get reduced here.
So R cannot be oxygen?
No, that would make it an ester. Yeah.
Any R besides oxygen.
That's right. So let's look at this structure. I've got 2 aldehydes. One is benzaldehyde, and one is off of a 2-carbon chain. Our reagents for Clemenson reduction, we'll use zinc with mercury in hydrochloric acid. Is this elemental zinc and elemental mercury, or is it ionic zinc and mercury? Elemental, and you know that because no charge is written, and they're not written next to a nonmetal or a polyatomic ion. I have two aldehydes. Here, they both get reduced. Can you give me a starting material that will produce this product?
One equivalent removes two.
One equivalent removes two.
Carbonyls?
Like we mentioned last week, hydrazine always in excess. So if I have multiple carbonyls, all carbonyls are reduced. The same thing is assumed here with our metals and acid, always in excess.
And you can't choose which one goes first.
You don't need to choose which one goes first. No. You can read into a physical organic chemistry textbook if you want to. That will give you your answer. Is there only one correct answer here? Okay. So, come up with as many correct starting materials as you can. Feel free to work with each other.
Well, you have 4 positions, and you have 2 groups that you can put on.
Only reduce.
It doesn't have to be 2, does it?
It's okay.
Why is this one capped? Oh, because oxygen's back. So, 1, 2, 3, 4. Is that
Good start.
Yeah, 4 factorial options.
Yep. There you go. Does anybody feel really confident? Good job. You know what? Yes. Mm-hmm. It's just not a very common motif. It's not a very common group, but it definitely does exist. There's still more options. Still more. Anybody really good with technology? Because I could really use a hand in keeping this screen on for more than 5 minutes. And I swear to God, the settings is set to 30 or 45 minutes. It doesn't matter. It's like I'm locked out.
YouTube video.
That sounds like a lot of work.
Black screen 10 hours.
Anybody have an answer that they want to draw on the board?
There are 24 options.
Okay. Anybody else? Good. Could it be here? Could it be here? Good. Could it be here? Could it be here? It is there already? Oh. You know what? I didn't even notice yours here. Oh, creative. I didn't notice on yours. Not a very common motif, but not impossible. Cameron's got a similar one. Feel free to put it up there.
Oh my god, it went on the bottom. I know.
Anybody else?
Yeah. Oh yeah, you're right.
Yeah. Killian took advantage of every single carbon in the product that could have been a carbonyl. A ketone, an aldehyde, an aldehyde. And he reduced all 4 of them down to their alkane structure. and didn't need to specify equivalences because we assume excess of our reagents. Whereas Jacobs focuses a little bit more realistically, if I may, on just one position. But I did see combinations where this aldehyde carbonyl was shifted up a position to be just a ketone, or to be a benzylic ketone, right off of the carbonyl, or sorry, right off of the aromatic ring. And then I saw one that had two ketones, alpha to each other, meaning they are adjacent. And then also one that had this aldehyde, or I guess two, that had this aldehyde and this aldehyde. Great combinations. What you're recognizing is that all aldehydes and ketones are reduced, and that ester never got reduced. Great. Any questions on Clemenson and Wolff-Kishner reductions?
Same effect.
Cooper and then Matt.
So with these, we're talking about how, even if they're not necessarily like benzoic, they'll reduce.
Correct. It's going to be useful as a benzylic position in our next section, section 16, which is why it gets introduced now. But unlike, and I'm sorry to hold you back, unlike radical halogenation, unlike alkene addition, unlike SN1 and SN2, these reactions aren't necessarily impacted in the same way by that benzylic position. Yeah? All right, your question?
It's kind of like the opposite side of that, but so are these also reactions we would see with other compounds when they have this sort of universal reducing power and we're just looking at them in relationship to benzene, or are they sort of specific to these groups in some way attached to a benzene?
No, it has nothing to do with the benzene.
Okay,
Yeah,
just has to do with these groups and these I guess reactions.
correct.
Okay.
So all of our examples have had the benzene ring in them. A benzene ring is not required for these reactions. Later in the semester, we'll have a unit on aldehydes and ketones, and we'll review this reaction and how it can be done without benzene rings. But in this unit, since we're focusing mostly on benzene rings, we're going to keep it in there. But that's a great question. To clarify, this aldehyde, not impacted by any means by the fact that there is a ring in this structure. It means nothing. Yeah. Matt.
So I was just wondering, the hydrogens that come in,
Thank you.
is it conjugate the carbon? Or
Reduce.
reduce?
Where did the...
I'm assuming they come from the acid. Are you going to talk about then what the metals do? Like how do they react with the ketone, the aldehyde to pull it off and allow that?
Great questions. So this is part of the mechanism, right? How is everything playing a role? So Matt, you nailed it on the head. I'm going from one hydrogen on this aldehyde to 3 hydrogens on this aldehyde. A 2 hydrogen reduction, right? Which we would call a 4 electron reduction. This carbon loses electrons in both bonds to oxygen, and now it gains electrons in both bonds, so it's a total of 4 electron reduction. The H's come from the acid. So even there, we need how many equivalences of acid? 2 per 1 reduction of an aldehyde or ketone. And we don't even explicitly say that because we assume it's in excess. Then what are the metals doing? If this is being reduced, what is being oxidized? Metals are great reducing agents because they are easily oxidized. Oxidation is what for electrons?
You give it away.
Loss, right? Oxidation is loss of electrons. Metals, in their elemental state, like to give away their electrons to become their ions. So some of the byproducts that you could expect here: zinc ions, which is often zinc 2+, mercury ions, which is either mercury plus or dimercury plus. Kind of a weird one. And what do you think is balancing those zinc and mercury ions? There's chloride, the oxygen that got lost. Yeah? O minus? No. O2 minus. So you may be getting some zinc oxide, some zinc chloride. You may be getting some mercury oxide, some mercury chloride. You may run this in water, since you've got that aqueous acid anyways, HCl, which means you may not get a precipitate. You may get most of it dissolved. I guess it depends on their solubilities. I think most things are soluble with chlorides, and I don't think either of these are insoluble with oxides. So it's just going to stay dissolved. And then you can run an extraction. Here's an organic, put in some diethyl ether, put in whatever you'd like. This is probably a liquid in and of itself. And then extract it into the organic layer for purification. Good question, Matt. But we're not going to look at the mechanism. Mechanisms with metals are pretty odd. They, showing how their electrons move is not very straightforward. I guess we can stay on this. I'll leave that up for you guys.
Is this type of reaction typically only done with like zinc and mercury and hydrochloric?
My understanding is that it's pretty much only done with zinc and mercury. There may be other metals that you can switch it for, and then it might not be called the Clemenson reduction, because I think Clemenson gets his name added to it because of the metals. We're actually going to talk about that in section 16. We've got these Friedel-Crafts reactions, acylation and alkylation, and there are other ways to acylate and alkylate, and they don't necessarily require the same reagents that the Friedel-Crafts does. So then I don't think they're named after them. Terrible. Why do we name them after people in the first place? Our last one here is our benzylic oxidation. I like this one because it's very straightforward. There are two oxidizers that we can use. One is chromic acid. We can write chromic acid as CrO3 in H2SO4. You will notice that that is not chromic acid. That is chromium trioxide in sulfuric acid. But they react together to produce chromic acid. Chromic acid is not a reagent you necessarily want to sit on, keep in your shelves. Chromium trioxide, easier to hang out with. Sulfuric acid, easier to store. Mix them together when you're ready to make chromic acid. You will see places that introduce this differently. You can also write this as potassium dichromate in sulfuric acid. If you don't want to hold on to chromium trioxide, you can get a hold of its salt, potassium dichromate, where they've been oxidized further. As you can see, there's more oxygens. And they've dimerized 2 chromiums in that structure. I'm only going to use the reagent on the left in lecture and on your materials. But if you are using the internet for exterior resources, maybe occasionally on active, you may see potassium dichromate. I want you guys to realize they are the same thing. 2 different ways of getting to the same product, which is actually H2CrO4. Chromic acid. We're just never actually going to write chromic acid. We're going to call it chromic acid, though. Is that okay? Our other oxidizer is potassium permanganate. And this we're going to write as KMnO4. I'm not going to require that you add this in, but potassium permanganate is a bit of a weaker oxidizer in this reaction. which means that and I'm going to write this in a different color so that you know it doesn't need to be shown, but sometimes it is. This requires a lot of heat, and it often needs to run for 24 hours until you've reached a good yield. Long time. It is a good oxidizer. We call it a strong oxidizer, but it's not necessarily fast.
So if we, I know this is like a little nitpicky, but if we did look at it and someone said heat over 10 hours, would we just expect half the reaction to be completed?
That's a good question. Reactions aren't necessarily linear. They're often the opposite of exponential. Not this, but asymptotic, logarithmic. They'll die off after a certain point. The principle of decaying outcome, what's that called? Diminishing returns. The law of diminishing returns. After a while, you're not actually getting much longer. You're not getting much more product. So it might be at 10 hours, maybe you're at 25%, and then at 15 hours, you're at 50%, and then at 20 hours, you're at 90%, and you're never going to get higher than 90 anyways, so then just cut it. It is a bit arbitrary, I would say, which is one of the reasons I don't always put it on there. I want you to pay attention to potassium permanganate. Which of these is a new reagent to you?
Chromic acid.
You haven't seen chromic acid. If you were in my OChem 1 class, you did see potassium permanganate. In the review that we did, we never used chromic acid yet, but we did use potassium permanganate. What was potassium permanganate used as? You could describe its role or the reaction.
Hold on.
We used hot and cold potassium permanganate, and it served the same function for different reactions and gave different functional groups. It was in oxidative cleavage, oxidation, and we used it in syn-diol addition, cold, which is also oxidation. You're adding oxygen to the carbon compound. So potassium permanganate has always been an oxidizer, will always be an oxidizer, but it's serving a lot of different roles. All right, one requirement. This reaction requires a benzylic hydrogen if there's going to be any sort of oxidation at that benzylic position. So I'm going to give us 3 different examples of alkyl groups.
You have to run the reaction for a day?
With potassium permanganate, you leave it boil for a day.
It doesn't have to be hot before you add it.
Why would that matter? It's not like a 24-hour timer where it turns off, you know? What happened? Methyl oxidized into what? A CO2H. What's that functional group? Good. Specifically here, a benzoic acid. So when you hear benzylic oxidation, the product will be benzoic acid. What happened to isopropyl? Oxidized into a benzoic acid. What happened to tert-butyl? No oxidation. The oxidizers need to first react with a benzylic hydrogen. They then create an intermediate that is stabilized by the aromatic ring. before they continue this process of removing groups and putting on oxygens. Yes?
Sorry, for the isopropyl, could you explain the loss of the other carbon?
We can try. So you recognize that with methyl, 1 carbon CH3 becomes 1 carbon CO2H. Isopropyl goes from CH3 2 to CO2H. We lost 2 carbon groups there. So what I like to point out is that these groups end up as this sort of char. They will also get oxidized in this process, but not being stabilized by the benzene ring. Their oxidation is not as clean, not as neat, not as useful. Textbooks don't really touch on what happens to those products. They just tell you, lob everything else off, ignore it. I reached out to a professor at CU Boulder to ask what happens. Her best explanation was, they just kind of end up as this organic char. Are you comfortable with that, Maddie?
I was about it.
Yeah. So here's a fun example. Ignoring the carbons that are lost during the benzylic oxidation, draw the product of this benzylic oxidation. Sometimes this would be worded as draw the major organic product, ignoring the other things.
I presume there'll be a trend of most of the reagents are going to be in excess in this class.
Yes.
So should we assume till you say otherwise?
Yes. Yeah, you should assume excess until otherwise. Good question. If you were interested in doing the mechanism, don't be. What is the intermediate that's stabilized by the benzene ring? It's a radical. And radical mechanisms are always so fun to draw. In fact, this mechanism is not exactly perfect. I would have added a second arrow at the CH bond that shows the 1 electron being kept by carbon. They don't necessarily show that. They also have an arrow that starts here that is not coming from anything but an atom. I tell you to always show relevant lone pairs. This is coming from a lone pair. Or a bond. Actually, it's coming from a bond, but it's not shown clearly. They could have been more careful there. This is just one part of it too. You can see that first it extracts a hydrogen, then it puts an oxygen on. Several more steps to follow. This is a reaction that I find to be not very intuitive. One that you just have to work to memorize, which is why this is not a mechanism that I will ask you to show. But it's a mechanism that I believe you could understand if you understand how the mechanisms we follow this semester work. If you understand that push and pull of electrons. Anybody want to draw their product up here? Or describe it? You want to describe it to me, Killian?
Benzene, and then have 2 carboxylics right off of it, right next to each other.
Good. You can draw them out. I'm going to abbreviate them just to save that space.
How would the carbonyls be oriented?
There's no wrong way necessarily to draw the carbonyls.
Can rotate?
They rotate around that sigma bond. Correct. So they can both rotate. You could draw them in several combinations of conformations. All right. Any questions? I like this example because it lets us take these bicyclic structures and cleave things off of them to make just a benzene ring. Pretty fun. By the way, this is called phthalic acid. this compound, where it's got this ortho dicarboxylic acid on benzene. Some of you might know of phenolphthalein. I believe it's related. This structure is a part of your phenolphthalein structure. All right, should we do some problems to apply some of these reactions that we've just learned? Yeah?
Is that chapter 15?
Section 15. Yep.
Phthalic acid.
Phthalic.
Is it 2 L's?
Yeah, I think so. Feel free to collaborate. Work with each other. If you feel strongly on one of them, find a classmate who doesn't, because as you teach them, you are bettering your own understanding of the material. So do it selfishly, if for no other reason. All right, Killian wants one more example, so I'm going to modify the structure we have here just a small amount. Because this will help me actually get the last reaction I needed. I do want to say one of these reactions on the board requires that you have at least some understanding of OCHEM1 reactions beyond the reactions we talked about just in section 15. Yeah, I held it. Yes, great. You what?
I didn't.
This reagent tells us what type of reaction is happening, or what functional group is needed in the front.
Oh, that's I don't know why I erased it, but it's in halogen. Wait, what?
Okay, yeah. If we didn't have H3O plus, don't forget your plus on there. H3O plus. Yeah. There you go. This tells us it's actually an alkene addition reaction. So we need an alkene in the starting material. If it was just H2O, I would go with you. It's substitution.
Okay.
But the H3O plus tells us
I forgot about that.
we're running addition.
Okay.
Good.
So,
Yup.
okay.
And no methyl. Perfect. What happened to your aromatic ring here? It's gone, correct?
Yeah.
You have no more aromatic ring. How easy do you think that is to do? It's not easy. No.
Yeah.
Because they love that aromaticity.
Mm-hmm. Is that
What's at this carbon?
an H?
There's an H.
Do I have to
Where'd the
state
H come from?
it came from?
That's right. It didn't. There's no reagent. There's no hydrogen in the reagent. Right?
Yeah.
So we have an H, a ghost H, that came from nowhere.
What did it come from?
Nope, it doesn't come from anywhere.
We just
Our product has an aromatic ring still.
Yeah.
Which means the bromine doesn't attach to the aromatic carbon. The bromine attaches to the benzylic carbon. Yep.
Okay.
There you go. No, you added a carbon. This one's right. Here, you added a CH2. You added a carbon. You need an alkene, that's right. But you have 2 carbons. Yes, that's a great intermediate. By the way, guys, when you're solving that multi-step synthesis, if you don't know the reagents, see if you can guess the intermediates. This is a good time for you to start turning around to the people near you and seeing what did they get that you didn't? What did you get that they didn't? Lean on each other to solve this synthesis.
So did that hydrogen? It didn't come from.
It came from nowhere.
Really?
It was unbalanced.
So it didn't come from like this
No,
carbon?
no, because you had a CH3 still. So it had all of its hydrogens. This has no hydrogen on it.
Yeah.
You added a bromine. This has no hydrogen on it, but you had a hydrogen there. This is right, but your double bond is still there, so it's still an aromatic ring.
Oh. Okay.
It's not an alkene reaction, and aromatic rings are not
I guess
alkenes.
it makes sense.
Correct. Good. Now, how many bromines added to the molecule? Just one. Where'd the other one go? There you go. You got it.
Okay, so that's I was wondering. It's like that's where the hydrogen went and went to the.
Right. You had that idea of something is supposed to happen with hydrogen.
Yeah.
It needs to go.
Before I erase it, is this impossible?
Yes.
Because that would.
Correct. That is impossible. Good job.
So I worked backwards. And so that the reagent for that set is the one missing. And that's what I've got so far.
Ah. Clever. You do know how to do that using Oken 1 reaction.
Oh, yes.
Oh, not this. No. When you have that ketone. You have lost a carbon. There was 1, 2, 3, and now there's 1, 2. That's cleavage.
This is a lot of.
That oxidized one of the carbons. That's oxidative cleavage. We did that in the Oken 1 review. Are there any benzylic hydrogens to allow for oxidation here? Remember, benzylic oxidation requires, did I erase it? Requires benzylic hydrogen. Is there a benzylic hydrogen? No. This is your benzylic carbon. It's a CO double bond. That's not benzylic, too far away. So, good thought. It's not going to allow us to do oxidation here, which is what I think you were aiming towards. Get to that ketone, then get to the carboxylic acid. If it does help, you know that nothing's changing here. So you know you're going to focus here on this intermediate. What could be here that gives you this? Work backwards. Word of advice to you guys, a reminder, if you will. I don't know that I did this much in our OCHEM 1 review. Steps for multi-step synthesis include brainstorming. Think about all the reactions you can use and all of the changes you're seeing that might be useful to have them in. Work forward and backwards. Don't just feel limited on taking a starting material and figuring out what it can become, but take a product and predict what it could come from. You have this structure here. Can you figure out what made it? That's very similar to what I had you do here. You have a structure. Can you figure out what could have made it? And you actually have a leg up because you know what's really possible. You know what is there beforehand. You've got options. The other thing that I say, I normally put this as number 1, but this is map your carbons. You don't really need to do it in this multi-step synthesis, but it can help you figure out if you're adding carbons to a structure or if you're removing carbons from a structure, and it can help you pinpoint where a reaction is happening. Okay, keep going. That's who you're working with.
Nobody yet.
Okay.
On those first two, am I?
Oh yeah. No. Here it looks like you're assuming the hydrogens get substituted by OH. Hydrogens are very hard to take off of a carbon. We talked in the last class about how they have a pKa around 60.
Right.
So there's no way OH or water bonds to it and takes off. This reagent should actually tell us we're looking at alkene addition. This is acid catalyzed
I think so. You have to add a carbonyl to it first,
by that
then you
name,
add the alcohol. Second step.
That's right. By that name, it tells you what to. You could keep your structure. It is 90% right. Oh wow! It's 90% right.
Is the CH on the top left? Is that carbon with the alcohol off of
Close.
it?
So now you've got
No,
a fire
that's
number.
that's an aldehyde.
Wow.
That's it.
So really, it's just about understanding that.
You can't. Well, and they're not disappearing. They go somewhere. But you really can't keep them off either. They're
I
very
only,
hard to
so I wasn't actually halfway through the video from the last one. It's like
Where
really
you
good
use
stuff
to do
for
that?
actions.
Very strong.
Based on what we just learned, I only got like the final one. Final step.
Although I like it, you know,
Oh,
it's
yeah.
this
You're on the right
one
track
is
here.
this
You
one.
hit a benzylic carbon. You add one carbon.
You know what I mean?
So you just leave off CH3, you make that a CH2BR, and that's your answer.
The BR is attached to the C.
Just like it is right now. But it's not
No, I think the aldehyde.
CH3BR to CH3. It goes from CH3 to CR.
CH2.
Yep.
Oh, no, I'm not saying it happens here. It's here, it's stable.
How many bromines in the reagent?
Here.
Here. How many bromines got
Why
added?
is this?
Where's the other bromine?
Is it a byproduct?
Yeah. And it takes with it something that leaves
I'm guessing
from
it's
carbon.
for an aldehyde.
Are you guys doing on the synthesis? No? This is not what's up there, by the way. It's not an alcohol.
I think maybe you don't want it. It will bump it up.
Because it's CHO, not CH2OH.
That one's
Okay.
Not in the first steps, no.
But there's also like if all the, yeah, that's not
Cameron.
the full source of oxygen.
It shows the wrong functional group to reduce. Hydrogen
I don't know, yeah, I guess we will.
is ineffective on carboxylic acids, only effective on aldehydes. And that's what CHO is. CHO is an aldehyde. No, none of, there's one reaction in there that we did last semester. Most of this is new stuff. Yeah.
I was like,
No, it's not gonna want that.
that makes more sense.
So hydrogen is part of the aldehyde.
Yeah.
We were just talking about it.
And here's the difference. The reagent given
Oh, I
out the
should've-
water
I
and
was supposed to take out the
if we're doing
That was my
substitution,
Oh,
we
okay.
don't
Because
need
that
acid.
just takes off the.
I don't know if we necessarily
But it
don't
just makes
want
it
acid, but we certainly don't need it.
Okay, that makes sense.
Just put
But
H2O.
I thought it was
The
like,
H2O
alcohol.
tells us
Yeah,
this
So, like,
is an acidic reaction.
yeah, okay, that makes
Right?
sense.
Acid catalyzed
For our
hydration,
Oh,
which is an alkene.
It just, should we just?
Yep.
Get rid of the.
So that's a good guess. I like that idea. But I want to see you connect acid catalyzed hydration reagents.
Some of the one confusing.
Yeah, I was like,
Yes, it's
cause like
like
you
a-
had the alcohol.
Yeah,
and then
yeah,
you
that
did
was
the
when I was
chromic
doing the
acid.
H2O plus.
So I was
Yeah,
like, okay,
thank
that
you.
makes-
What is this? Is it an H or a two bonds? Yeah. I feel like it's two bonds, but it doesn't look like any of your other double bonds. It actually looks more like your H. So I'm not sure. But this is a great process. That's exactly what I was going for. They're the same family, platinum and palladium and nickel will all run hydrogenation. It works.
just do like diatomic hydrogen too, or does it need to be?
If you put H2, I would want you like half off on the reagent.
Okay,
You don't have the catalyst.
so it needs the palladium catalyst.
Yeah. Or very, very high heat pressure.
Okay.
Yeah. Can I see yours? You got a 5 bonded carbon here. Yes, exactly it. And that's it. That's great.
Oxymercuration?
Exactly. Perfect. Work.
Oh, yeah, no, yeah, no.
This is a good guess. You're showing a type of reduction.
How do you carbonyl something?
Well, you need to get,
Carboxylic
what they told
acids
us.
are
You need to get rid of the double bond.
and that's what gives it CH2O.
Make it carbonyl.
And make it so you can
Not
do
alcohol,
the reaction,
all the way
put
down
the
to
carbonyl.
alkane.
So make the alcohol first?
You bet.
Yeah, so what they had done is they did
Perfect.
So,
H2 over palladium
I'm just curious.
to eliminate the double bond.
You can just put an alcohol there right now.
Well, no. I mean, you could. There might be. Yeah, you could. There might be a reagent. Well, yeah. I don't know of a reaction that would just add on.
Great question. Yes.
Yeah, that's what I'm asking.
Got
So-
the idea there.
There might be reagent. I don't know what it is, but
Not
from what they
Okay,
did.
so actually, you have pointed out a good point that I wasn't aiming for because I didn't have that aldehyde on there first at the start, which is that aldehydes can be oxidized to carboxylic acids and silic acid. So it wouldn't work. Yeah, it doesn't work as I showed it. And I was, I was thinking of actually doing it the other way.
They got rid of the
Yeah, that's a good point. So
just
if
have
you
to
want to show something different, if you want to show the real answer, this doesn't exist anymore, even though that's what I showed. it becomes a carboxylic acid instead of staying an aldehyde. This is an aldehyde, which means that after this, if there's two carboxylic acids, nothing happens. But you followed it exactly the way I was hoping you would, and you pointed out my mistake. Same thing for you guys. You guys thinking? Yeah. So this being a carbonyl means we won't be able to oxidize it to a carboxylic acid because we'll need a benzylic hydrogen in order to bond benzylic. So this is a good idea, but it's not going to set us up for oxidizing to
And what they need is a benzylic hydrogen to put on to make that isopropyl.
What are reactions that help us put hydrogen on the
Carboxylic acid.
hydrogenation? Exactly. Now I do want to point out, maybe your program is showing it as COH even if you type it as CHO. I wrote it explicitly as CHO on purpose because whether it's to the left or to the right, that's how we abbreviate.
You'd only have zinc.
So you could just put in a double bond and you have your aldehyde.
This is a metal and acid that we're looking for.
Correct.
Yeah, with the isopropyl group. They were doing
Good. Yeah,
chromic
that would be the
acid.
carboxylic acid.
Add your
And then in that last step,
carboxylic group. And then
okay.
your Wolff-Kishner
All right.
reaction.
Why don't we go through these answers together?
Well, he was explaining.
And I'm going to point out a fatal flaw that I have in this. It's a flaw that we're going to talk more about later in the semester, not necessarily this soon. You likely followed my thought process correctly, but I have misled you with this question. So that's my fault. It only happens like once per exam, I swear. First of all, we see that there is this CHO group that does not change over the course of these two reactions. What is that CHO group? It's an aldehyde, although you're used to seeing it written the other way. It's just flipped here. It's written with the same intention. Carbon is bonded to that hydrogen and also to that oxygen. That's why I flipped it the way that I did. To make it intentional. So we've got an aldehyde. Something changes, but obviously not the aldehyde. That sets us up for doing a benzylic carboxylic acid, create a benzoic acid. And I know that it's giving me a carboxylic acid in this second step because there's no benzylic hydrogen here to allow for oxidation. I can't do benzylic oxidation yet. So, I have no benzylic hydrogen. To give me oxidation. So what do I need? I need to add hydrogens. Remove the alkene is a bit ambiguous. Can I do alcohol? Can I do H3O+? No, because that's going to put the OH at the benzylic position, which means I still don't have a benzylic hydrogen. Could I do Br2? No, still no benzylic hydrogen. You could argue that you could do hydroboration oxidation, because anti-Markovnikov means that would put the hydrogen on the more substituted carbon. You can argue that you could do anti-Markovnikov HBr, radical HBr, in peroxides, because that would put the hydrogen on the more substituted position. But the easiest way to get hydrogen there is just to add hydrogen by hydrogenation.
Are there ways to swap that methyl group to carbonyl?
Yeah, you can do oxidative cleavage and make a ketone
Don't you need an alkane or alkene or alkyne for that?
There is an alkene. You would cut off this carbon, and you would have a ketone with here carbonyl here. That carbonyl cannot be oxidized because there's no benzylic hydrogen.
So you wouldn't be able to make alcohol.
It still wouldn't. It's not an alcohol. Still wouldn't make a carboxylic acid.
You wouldn't be able to add the hydroxyl group.
Carboxyl group.
Carboxyl?
It's not hydroxyl because it's not an alcohol.
It is.
It's best to call it a hydroxyl group, a carboxyl group. So we get our hydrogenation product, which now can go through oxidation. I'm going to put chromic acid. And this is where my fatal flaw is. If you were following my thought process, then you understood hydrogenate, oxidize. We get this carboxylic acid and aldehyde with Wolff-Kishner reduction, which gives us meta-methyl benzoic acid, which, by the way, you can combine the common names of toluene and benzoic acid, and you can call it toluic acid. I know, it's a stretch. I think it's better to call it M-methyl benzoic acid, but you can call it M-toluic acid as well. In fact, those of you in lab, you will synthesize DEET, which starts with, I think, M-toluic acid, or maybe O-toluic acid. Here's the problem. That was the thought process, but and this is later, so this is not what you're going to be tested on coming up with this unit test. This strong oxidizer is reactive to aldehydes. You pointed out that it's a benzylic hydrogen on that aldehyde, which is kind of true and kind of not. It is on a benzylic carbon, but it's not the same as most benzylic hydrogens because it's attached to that carbonyl. But all aldehydes are reactive to this oxidizing agent. All aldehydes would have become a carboxylic acid. That was not the intention. And that's my fault because I wanted to do the hydrazine. I just added on the compound late. What would happen in this last step if we showed the true product? Nothing. And we could write that as NR, stands for no reaction. Yeah. So that's my fault. Bit of a learning lesson. We're going to talk about oxidation of aldehydes in the aldehyde unit. So don't pay attention to that. If you followed the thought process, you were on the right track. Does that make sense? Okay. Why don't we take a 5-minute break, even if you're not leaving. Stand up, get your blood flowing. Somebody come help me with my computer. I'll give you a high five. Thank you.
So it's just that the screen's locking too fast?
I want it to lock later, you know? I want it to lock in like half an hour.
Should be pretty easy to find.
You'd think, right?
Is it just the timeout?
I think so, but it honestly makes me feel like I'm stupid because no matter what I try to do, it doesn't like it.
Do you think your parents would be able to figure it out?
No, I don't think my parents could figure it out. So I even Googled it. This is what it says to do.
Yeah.
Screen, sleep, and hibernate times. Turn my screen off after 30 minutes.
That is this monitor specifically. That doesn't refer to locking your screen.
Okay, where do I go?
That's a very good question.
Isn't that my monitor? What do you mean? Locking my screen and locking my monitor are different?
So turning off the screen is like turning off a TV that's connected to your computer. Like it's not actually doing the thing that makes it lock and go to the login screen.
Okay. Here's what I think. This is a college computer.
There's some kind of profile that's making you log out.
Exactly.
Mm-hmm.
I've never seen any college, of all the classes I've taken, I've never seen it stay on. It's the same problem in every class.
It bugs me to no end.
It's horrible.
and you see me walk over to like point at the screen, and then it goes off, and I'm like, what the?
Say what?
It's on that screen timeout setting.
I think that's where we were just looking.
That's your job.
Yeah.
You might not be able to see the board, but
Oh yeah.
Yeah.
I wonder if it has anything to do with like the actual. So you plug it in.
no, it's not when it's plugged. Like even when I'm at home, just working in my office, just working on it, not plugged into any extended monitors, does the same thing.
So when it goes quiet here, does it also go quiet on the laptop, or is it just the projector?
You mean like when it locks
When
here?
it locks here.
It locks. It's just showing you my screen.
So it's not the projector, it's the computer.
It's not the projector. It's my computer. It just locks every 5 minutes.
We should try the 10-hour black screen video. Put it on another tab.
Yeah, I'm not trying to run more power on my laptop at any time than I need to.
It's very low power.
I was gonna say, is he on save battery mode? I should also check that.
I'm not.
Okay.
And I turned that off because I wanted it to stay on. I do think the college, though, has some sort of programmed thing where it's like, well, imagine, they don't want students to get into my profile because then they have access to
That shouldn't be it.
my computer.
It's the same way at Intermountain, everything times out, just like
Yeah,
that.
and
You can't control it, because they don't want patient information.
Yeah. Although then they should have it.
I feel so bad for them because they'll be even typing it. And it'll go.
But at least there, they have their badge, and they can just badge in real quick.
On the computer?
Yeah, so you just walk up and you just badge in, and you're in.
And you guys see me type my password. It's so long
Yeah, we know your password.
that I mess it up every time because it's too long. And
Wired password or did you?
it's like a good password, it's a strong password.
Is it a really long chemical?
I think it's got 12 characters.
Yeah.
It's got 12 characters, a capital, a number, a special.
Some alkynes, some alkenes, other functional groups.
Maybe a carboxylic
It's M-methyl-toluic acid with an exclamation point for the I.
10 minutes.
And then Raj sits down. Classic. Kind of.
That shouldn't be it.
Too
10 minutes is too
Hint.
long.
Precursor to D.
We're gonna try that.
Are you staying after class today?
No. You have questions?
Do you think he could solve it by getting Linux?
By getting lit?
Yeah. Switch to Linux.
That
Yeah.
would make a difference.
My rule
I don't know what kind of difference. What flavor of Linux?
when a bond breaks,
I don't know Linux.
That's a solid one. Yeah.
more electronegative.
I haven't really touched Linux in a long time, but I've spent a fair bit of time with Mint, a little bit with Ubuntu. I had a class we used Kali for.
Carbon.
That was an interesting one.
So you're showing carbon taking electrons from oxygen.
Okay.
Good. When a bond forms, it forms from the more electronegative atom. Who has electrons to share?
School thing.
Partial negative atoms.
I don't think changing it to Linux.
You want to form a bond to
So I tried a thing. I figured we would see
carbon,
if
it's got to come from oxygen. You want to break a bond between this carbon and oxygen?
The
It's
10-hour
gotta
black
go
screen.
You guys would choose
bonds break to partial negative.
to see.
Bonds form.
Yeah.
Like when you would hate you.
Yeah.
Well, there's two other things. You are breaking or you want to
Everybody's got this like,
you're not going to have a
feel like you. I'm not a fan of this like floppy shoe on the back, but I kind of like.
and then what you're doing here is just putting a lone pair on carbon, taking a lone pair on carbon. It's like you're going to put negative on carbon and positive on
Does it have a Vibram?
So you recognize you want to make a benzene type ring. It's got to come from oxygen to make that double bond. And
Well,
when a bond
that's
breaks,
how I feel
it's
with
gotta go
those things.
to oxygen.
So, you know.
I promise you, you've never seen a correct resonance where a CO double bond breaks away from
crap and then it's broken. And then
CO double bond always breaks two.
I'm just starting a new job actually.
And that might
Doing
be
some kitchen tech
incorrect,
stuff.
they might have summarized things incorrectly.
On the move a lot, so I was like,
Or you might be. I need to see your example. So can I try to draw it out?
Yeah.
Yeah, sure. I'll have to look into it.
Yeah, where's your new job? IMC, big one?
Yeah.
Here's acetone.
Yeah. That'll be cool.
Here's a resonance structure of acetone.
Yeah, it's spring.
Yeah, likewise.
Yeah.
How would you draw arrows?
That'll be a great experience.
Yeah, I spent a lot of
On the
time
left
working
to form the right.
there
This is how
on the
it's done.
administration side, so this will be kind of a cool, whole circle to go back.
Because the CO double bond breaks. So you need to start at the double
So
bond.
you're saying he's doing that.
That's correct.
Okay.
Let's look at
Something that kind of works.
let's look at this thing.
Going to school and being flexible.
Here's a resonance form.
But
An
eventually
enole.
want emergency medicine, so maybe
Can you draw arrows here
traumas
to form this?
and the ED. Super exciting.
Oh, are you gonna be in the year you floated around the water?
You kind of float around the whole hospital.
Be your break,
You can ask
I know it feels that way.
but it's not.
So why don't you start on the form? The bond that forms.
a little bit of everything.
What arrows do you need?
Sometimes I'm noticing it's hard to shout out.
You see the CC double bond break.
It's hard to
You
contact
see
those
the CO
dots.
double bond
Nature
form.
of it.
When bonds break, they break towards the more negative. What's more negative? Carbon or carbon? Carbon. When a bond forms, they form from.
Yeah.
When a bond forms, it forms from
Yeah. And usually it's just shut up.
the negative. The thing that has an electron. I need to form this bond. It needs to come from oxygen. Well, that's not the bond that breaks. This is. You got this right. Start from that. Make a chart. Show the double bond. Moving to this region. You have that break arrow. Exactly right. Perfect. This bond breaks. So start from this bond. You can't go here because that's that.
Because if you know you're going to do
And actually, we do say less substituted carbons are more negative, more substituted carbons are more positive. That's why Mark Hodgkinoff's rule works. H adds to the carbon with less H. Carbocation forms on the more substituted carbons. More substituted, more positive, more stable, very positive. This is where you can come from and home. If you're going to make a double bond. But if you're going to break a double bond, oxygen already sizzle like this. If you find those resources, show them to me. That's okay, me too. That's why I've got this up. If you do find anything, let me know. But otherwise, follow this idea. Good. Oh, we didn't finish these. I do want to point out a common misconception I saw on this one, which was doing substitution with this reaction. You recognize H2O as a weak base, weak nucleophile to run SN1. But the H3O plus tells us that we're doing an acid catalyzed hydration reaction. Acid catalyzed hydration means we need an alkene starting material. So I would have given partial credit for a substitution here, but removed partial credit for not recognizing the role of H3O plus. Now, the other misconception I saw here was people putting the double bond at this position, which breaks the octet at the carbon in the ring, gives it 5 bonds, which you can't easily see because it's got the circle. The correct placement of the double bond is here. And again, this highlights how on benzylic positions, Markovnikov's rule doesn't always hold. This is the more substituted position, and usually H goes to the carbon that is less substituted, but this time H went to the more substituted because the carbocation is more stable at the benzylic position. The carbocation gets delocalized into the ring through conjugation. Here, I put that bromine on the ring to kind of confuse you, to throw you off. But there is a benzylic hydrogen, and this is what the bromine can react with. Bromine radical takes a hydrogen away. Carbon radical delocalizes through the ring. I think there is only one wrong answer, and I do want to talk about it. And this was this product. I understand the thought process here. I've got a bromine on the ring. I'm going to put another bromine on the ring. And something about the benzylic carbon, so I'll go to that position. But here's what I pointed out. Yes, we added a bromine here, but we accidentally added a hydrogen. Where would hydrogen come from? No hydrogen in the reagent. CH3 stays CH3. So it's not like one of the benzylic hydrogens is transferring. Ghost hydrogen becomes invented here. So you can always try to spot check. Look to see if you've got any stoichiometry that doesn't really add up or make a lot of sense. All right. Good work. We are officially done with section 15. We're going to move on to section 16.
What's that bromine right off the ring's position called?
Allylic. Because it's no longer an aromatic ring. We stay in the world of benzene. But now we run aromatic substitution. This is not SN1. This is not SN2. This is SNAR. Sometimes. Which is also called NAS. And this is EAS. There are two ways in which you can substitute a group on the aromatic ring. Oops, that's not psi, that's just Y. So to generalize, we can say some group Y gets substituted by some group Z, and aromaticity unchanged. Why would you want to change aromaticity? I do want to point out, there are ways that you can get rid of an aromatic ring. You can reduce an aromatic ring. You can add hydrogens to it. It does some strange things. It takes a lot of heat and it takes a lot of pressure, along with palladium or platinum or zinc or nickel. There we go. Yeah, please. Anything. I'm not gonna spend time covering reduction of aromatic rings, but you may see them if you look at different reactions. The nice thing is you can't accidentally reduce an aromatic ring. You have to actively try for it. So in this example where we had reduction of the alkene, hydrogenation of the alkene, you would need to increase the temperature quite a bit, increase the pressure quite a bit if you wanted to do anything to that alkene. The reactions we're going to pay more attention to involve this substitution. There is an intermediate, no matter what reaction you have. That intermediate is sometimes called the sigma complex. But depending on the nature of your substitution, that sigma complex has a different charge. So I'm going to generalize this again. This structure has either a positive or negative charge. If this is too confusing as a generic thing, you may ignore it, because we're going to show the mechanisms over and over, and it will be either positive or negative. Thank you, Nayira. We'll see how it goes. Do you understand what I'm trying to abbreviate, though? Is that it's one or the other, and it depends on the nature. Then it collapses back into an aromatic ring. This is the intermediate, and we call it the sigma complex intermediate. The aromatic ring as a nucleophile. What does that mean? Nope.
It has electron one status.
It's the electron donor. The aromatic ring shares its electrons. What charge would that give it? Positive. Because the ring is giving away its electrons, it takes on a more positive charge. These are the electrophilic aromatic substitution reactions, otherwise called EAS. It's in the sport, or it's in the game. That feels confusing, doesn't it? When the aromatic ring acts as a nucleophile, we call it electrophilic aromatic substitution. Did I make a mistake? Again? No, we read it backwards. Substitute the aromatic ring with an electrophile. The ring is being substituted electrophilically. An electrophile is being put onto the ring. So the ring must act as a nucleophile. Ring donates electrons, takes on a positive charge. There are, and I've got this on your learning objectives list so that you don't need to guess. There are 6 EAS reactions that we're going to learn. Adding bromine, chlorine, alkyl groups, acyl groups, nitro groups, and sulfonyl groups. But you may not have just benzene as a precursor. You may have a substituted benzene as a precursor. Substituents can increase nucleophilicity. I'm going to abbreviate that with increase nuc minus. Substituents can make the ring a better nucleophile. That means it takes less energy for the reaction to occur. The reaction is activated. These we call activators. Or they can decrease nucleophilicity, which we call deactivators. No. There are two ways that you can substitute the ring. Here's your sigma complex in the middle. This is a brief energy diagram. If you have an activator, it takes less energy to run the reaction. We're going to name those substituents. We're going to learn which ones do what. If you have a deactivator, it takes more energy to run the reaction. Make sense? Do you activate the ring for being a nucleophile, or do you deactivate the ring? And we're going to talk about why certain groups lower this sigma complex and lower this barrier of activation. And we'll talk about why certain groups increase this barrier of activation. And then this is where it gets really fun. Substituents can direct the ring's nucleophilicity. A certain substituent can make the ring a better nucleophile to positions relative to itself, to positions that are ortho and para, or to positions that are meta. So we develop ortho-para directors and meta directors. And then we get these combinations. Some groups are activators that are ortho-para directors. I want to take that back. All groups that are activators are ortho-para directors. There are some groups that are deactivators that are also ortho-para directors. And then there are groups that are deactivators that are meta directors. And we're going to talk about which groups go into what families. I want to introduce these substituents and put them into their families. However, we are in the context of EAS. All of the information that we talk about here turns on its head when we look at NAS, nucleophilic aromatic substitution. The ring is substituted by a nucleophile. The ring accepts electrons and takes on a negative charge. Some substituents still increase electrophilicity. It's those that are deactivators in EAS. Some decrease electrophilicity. It's those that are activators in EAS. So the groups that play one role in EAS reactions play the exact opposite role in NAS. So when going through these learning objectives, by the way, you'll see on the second page that it says, apply substituent directing and activating effects on EAS and NAS. It's crucial that you first identify what reaction am I covering. I think what we've got time for today is just getting familiar with our groups and putting them into these categories for EAS, which is where it's most relevant anyways. We're going to come back to talk about NAS next week. So if you need to, leave that note. This info is for EAS reactions only. We'll talk about EAS later on. Three families.
Orthopara?
That's right. Oh, thank you. I put directions, but I meant directors. Deactivators. I spelled that right. Most of our activators are carbon and oxygen groups bonded to the ring. And I'm going to rank them in order of activating strength. So strongest at the top. The first are nitrogen groups. And I like to give some examples to clarify the breadth of nitrogen groups that you can have that act as activators. You could have NH2 attached to your aromatic ring. That's aniline. Yeah, I had to make sure it wasn't alanine. You could have dimethyl aniline. Doesn't need to be two hydrogens. Or you could have an aromatic amide. Because that's still a nitrogen next to the aromatic ring. Why do you suppose this nitrogen group increases nucleophilicity in the ring? Why does it make the ring better at sharing its electrons? That's right. These nitrogens have a lone pair directly adjacent to the ring that they can conjugate to the ring and offer for the ring to use. Hey ring, you need to use your electrons to attack an electrophile? Borrow mine. That's what it does. Same thing with OR groups. And this may feel confusing, but in this family we're going to have phenol, where R is H.
So when it says R2, it could be two separate atoms.
Yeah, like here, where it's an amide and a hydrogen. Phenol, anisole, methoxybenzene. Similar to the amide, we could also have an ester connected via the oxygen. How does this increase nucleophilicity to the ring? Conjugates its lone pairs. Oxygen's lone pair donates to the ring, gives it more gives it more nucleophilic power. Why is this not as strong of a donor as nitrogen? Why does nitrogen increase the ring's nucleophilic power more? Exactly. Nitrogen shares better. Nitrogen gives away its electrons more willingly than oxygen. Most people think of oxygen as the big electron guy. Yeah, that's exactly it. It doesn't want to give away its electrons. Nitrogen does that better. The last group that we have here is alkyl. And alkyl is really just methyl, tert-butyl, etc. All of those hydrocarbon chains, those are our alkyl groups. Why are these the least activating of this series? The carbons don't have electrons to donate. They don't have a lone pair. What they're donating is what I call moral support. They've got a cloud of electrons that they don't care much for, that they can push towards the ring, and the ring can be supported in its efforts, but it doesn't have any borrowing power. I want to jump over to the deactivators. These are acyl groups. And now here's the deal. I am going to pay attention to the strength of activators. I'm not going to pay attention to the strength of deactivators. Because in EAS, it's less important, the strength of the deactivator. It's more important, the strength of the activator, how things get substituted. Do you know what I mean? If a nitrogen group activates a ring the strongest and directs the ring orthopara to itself, guess where the ring is going to react from? Orthopara to that strongest activator. If a group is deactivating the ring, who cares? It's not encouraging the ring to react, so it's not directing how the ring reacts. If a deactivator needs to direct at this energy, then the ring is going to be directed at this energy. Activators, the strongest activators, play the role as the director. We'll talk more about that. Acyl groups are one of our deactivators, not necessarily the strongest deactivator. But I put this up here because they've got the most examples, so I want you to be able to see them well. Where'd my green go? Do you know what acyl is? Acetylcholine, acetic acid. Acyl is a carbonyl group. So when you see carbonyl, you can think acyl. When you see acyl, you can think carbonyl. So here are some carbonyl groups. What's that? That's an amide. Oh shoot, did I make another mistake? Can amides be both activators and deactivators? Correct. It all depends on how they're attached. The nitrogen can't share its lone pair. It's not adjacent to the ring. Actually, this carbonyl can take electrons towards the oxygen and is going to ask the ring to foot the bill. What's that going to do to the nature of the ring? Charge-wise. Makes it more positive. How good is a nucleophile that's positively charged? Not very good. We can have esters. Why is that different? It's connected opposite. Oxygen cannot donate its lone pair. You can try. Go ahead and try. Oxygen shares its lone pair here, breaks the octet at the carbonyl carbon. Carbonyl carbon needs to break a bond. Well, you either break the sigma bond and now you don't have an aryl ester, or you break the CO bond to the oxygen, you didn't get any electrons to the ring. This does the same thing. It pulls electrons out of the group. But now we can expand it to some other acyl groups. We can have an aldehyde. We can have ketones. We can have carboxylic acids. We can have anhydrides. We can have acid halides. The nitrile is technically in this family. It's not really considered an acyl group all the time, but it's often thought of in a similar family. So you could even put the nitrile here. Some of the other groups, nitro and sulfonyl groups. I'm just putting them together because I'm running out of space. I'm going to show you nitro expanded. We often write nitro as NO2 because it's just easier to write that way. But when you expand the nitro group, you realize that it's actually constantly in resonance with itself. That negative charge is delocalized across two oxygens, and the nitrogen always holds a positive. But I'm drawing one of its resonance forms, not the resonance hybrid. It's a Zwitter ion. It's neutral with balancing charges. Why does this pull electrons from the ring? Because of that same double bond to the oxygen, asking for electrons from the ring to put them in. And here's our sulfonyl group, aromatic ring, 2 SO double bonds, and SOH. Remember that sulfur can expand its octet. This does the same thing, asks for electrons from the ring to give to one of the SO double bonds. Now we have some very nice names for these groups. Groups that very clearly donate electrons, we call electron donating groups, and we abbreviate it as EDG. Groups that pull electrons from the ring are electron withdrawing groups, and we call them EWGs. We've got this family in the middle that actually does a bit of both. Donates electrons in some ways, but pulls electron density in other ways. So it's harder to give this other family such a cute little name. Can you guess what it is? No, we're actually not going to call it an electron anything group. Because it's in the middle, it plays both sides, we can't really call it donating or withdrawing. These are electron groups. No, come on, guys. I'll give you a hint. Look at all of our EAS reactions and the functional groups we've got. We've got alkylation, acylation, nitration, sulfonation. We don't have halogens. We've got every other functional group imaginable here, but we don't have halogens. The acid chloride is not directly bonded to the aromatic ring, so the chlorine is not an aryl halide there. So this last family is just the halogens, so we don't have to call it electron anything group. And the challenge here is that these halogens do two things. They have lone pairs. I'm going to show it in black. Just like oxygen and nitrogen, that they can share to the ring. But they also have this very insignificant dipole that pulls electron density away from the ring. So it is a battle. It doesn't make the ring more reactive, but it stabilizes the sigma complex in the same way that these groups do. And I'm going to repeat that. Activating and deactivating is all about this energy here, which has to do with this. Do you push electrons in or do you pull electrons out? Halogens pull electrons out, which is why we call them deactivators. The directing effect has to do with this here. Whether you direct ortho and para, or whether you direct meta, has everything to do with how these groups interact with our sigma complex. Where'd my sigma complex go? I erased it. So, there's two things to pay attention to: the activation energy and the direction in the sigma complex. That's what we're paying attention to. When we come back next week, I'm going to start us off with just benzene reactions. And we're going to learn the reagents for these 6 EAS reactions. Then we're going to look at the mechanisms for those 6 EAS reactions. Then we're going to start substituting benzene. And we're going to look at the reactions when they have EDGs, EWGs, and halogens. And we're going to see how that changes the intermediates, changes the mechanism. We're going to see how that impacts direction. This is how we explain activation. The mechanism is where we can explain directing effects. We need to show that sigma complex to understand directing effects. Then we'll talk about NAS, which is going to go by in a flash because it's much simpler. Some of these rules don't even allow for NAS to occur. NAS goes by much quicker. The mechanisms are the same, if not easier. And the reagents are much easier as well. So NAS we'll do very quickly. And then we're going to piece all of them together. We're going to do multi-step synthesis with these and with benzylic reactions. All right. Have a great weekend. Thank you for your time. I will see you on Tuesday.
It lasted longer, didn't it?
Lasted longer than what?
You only had to do it once in 25, 30 minutes.